Okay, so this is showing you how to calculate chi-squared for a 2 by 2 table. So the data is that we're analysing an outbreak where 49 out of 250 children who ate cucumber fell ill and 4 out of 124 who did not. So we're going to need 3 2 by 2 tables. And the first one is the observations of the data, what actually happened. And we're going to set it up like this with ill, yes and no, and cucumber, yes and no. So we're told we need to give ourselves total for the row, total for the column. We're told that 49 out of 250 who ate cucumber fell ill, and also 4 out of 124 who did not. So we can fill in the rest by adding and subtracting. It's 374, that must be 201, that must be 120, that must be 321. So that's how things actually fell out. Our next table needs to show what would have happened if there was no association between eating cucumber and falling ill. So the next table is what would have happened. If the cucumber is completely innocent, it is still true that 250 people ate cucumber. It is still true that 53 people fell ill. So the totals out there don't change. You can just write them down again. And because it's a 2 by 2 table, if we can get this one number, we can fill in the others by subtraction. So the number we want is how many people who ate cucumber would have fallen ill if there's absolutely no association between eating cucumber and falling ill. Well, let's go back to the first table. Overall, 53 out of 374 people fell ill, and that's about 14%. So if eating cucumber makes no difference, 14%, that's 53 over 374, of these 250 people who ate cucumber would have fallen ill. So if the cucumber's innocent, this number here is 14% of the 250. It's 53 divided by 374 times the total number of people who ate cucumber. That's why this is the trick I'm about to show you works. So if you don't want the maths, the trick is you take this number, you multiply it by that, and you divide by that. And that gives you this number here. If you use the calculator, you'll find that 53 times 250 over 374 equals 35.4. As I say, the explanation for that is that overall 53 over 374 people fell ill, and then you multiply that by the total number of cucumber eaters. That's how it works. So now we can fill in the rest of this table just by subtraction. It's 2.6, 17.6, 106.4. Okay, so that's what would have happened if the cucumber is innocent. These two tables of data are clearly different. And now we're going to do a difference table. So this is our last 2 by 2 table. It's going to have 4 elements to it. And we're going to focus first on this difference here between 35.4 and 49. Well, that's a difference of 13.6. But is it plus 13.6 or minus 13.6? Well, we're going to do what statisticians always do when they don't know whether to make it a plus or a minus. We're going to square it. So the number here is 13.6 squared. And then we need to express that. Well, is that a big number or a small number? Well, if this table here is full of numbers in their thousands, that's a tiny number. If this table here is full of numbers like 10 and 12, then it's a huge number. So in other words, we need to put this difference in relation to what we were expecting. We're going to divide that by 35.4. Now here, and then we need to do exactly the same for the other three numbers. We need to look at what's the difference here between that number and that, between this and that, between this and that. We need to do that 4 times. But we can save ourselves some time here because this number, the numerator, is going to be the same in all 4 cells. That's mathematically certain to happen. So we can write that down 4 times. And the denominator in red is simply the red table repeated. So I'm just rewriting this red table down. Now, if you look at what we've done there, what we've done here is the top number is what we observed minus what we expected to happen squared divided by what we expected to happen. It's observed minus expected squared divided by expected, which is of course the formula for chi-squared. So if we add these 4 numbers up, we get the total chi-squared, which in this case, here's one I've prepared before, turns out to be 18.26. So that's the value that chi-squared takes on this set of data. The issue now is, how big is this chi-squared? How often do we see a chi-squared as big as 18 and a bit? Does that happen all the time? Does that happen once a month, once a year, once a century? So what we're really asking is, how big is the value of chi-squared that it only reaches 5 times in 100? What is the 5% cut-off value for chi-squared in a 2x2 table? And the answer is, there's a reason why chi-squared is called chi-squared. The 5% cut-off value is 1.96 squared, and that's 3.84. So the 5% cut-off value for chi-squared in a 2x2 table is 1.96 squared, which is 3.84. And clearly, the value that chi-squared has taken on this data set is far greater than the 5% cutoff value. So we say that the difference between what we observed and what would have happened if the cucumber is innocent is far too great to ascribe to chance. We conclude there is a statistically significant association between eating cucumber and falling ill. That does not mean to say that it was the cucumber that was contaminated, because it could have been the mayonnaise on the cucumber that was the problem. But statistically, we've executed and interpreted a chi-squared test. Thank you, ladies and gentlemen.